Hello, hello. Yes, now this is working. Welcome everybody to SQA Conference 2025 in Delft. We are very excited to have you here, and we are very excited to welcome you to Delft and to this conference where we will talk about superconducting qubits and algorithms and all the good things that are in that area. Before we really get into all the details of the conference, I will start now, give a short introduction to the conference and what we are going to do for the next few days. Before that, though, I think it's very, very important that we thank all of the companies that are listed here. They are supporting the conference, and they're the reason that you can get free lunch the next few days, you can get drinks, and we have a nice conference dinner later in the week. So if you meet anybody from these companies, say thank you for supporting the conference, because it really means a lot. Next, another important aspect that I think it's important to bring up front is the code of conduct for the conference. So at SQA, we are an open scientific exchange, and we respect everybody here, and we want to create an open environment. So please keep it colloquial, and if you see anything that make you feel unsafe, contact me or some of the other people from the organizing committee. They will mostly have white t-shirts or one of these hats, so you can recognize us. With that, let's get into short introduction to Delft and where we are going this week. So Delft is a small Dutch town, as you may have noticed. It's a historical town. Just an example of the sort of history. This church they started the construction in 1396, so that's many, many years ago, of course. And actually, this is the church where we will have the conference dinner. So you really get to see the sort of historic nature of Delft in this conference. Delft is also historic in superconducting qubits. Actually, the world's first flux qubit, which is a picture here, was made in Delft, in university, where some of you will get to see in the tours later this week. It's also in Delft that Europe's first cloud quantum computer was made back in 2020, so that's not so many years ago. But that was put online by a collaboration in Delft, and many of the people involved in making this quantum computer are now running companies in Delft and selling all the things that you can do or use to build a quantum computer. In fact, this is all the spin-offs that we have coming out of Delft Technical University, and in Delft, we have the so-called House of Quantum, which is a sort of incubator for a lot of quantum companies. We also have all of these companies present, which means that if you count people at QTech, at all of these companies, plus a few extra at different faculties and different research institutes in Delft, there's more than 1,000 people in Delft working on quantum. And Delft is a city with around 100,000 people, which I think makes Delft the highest density of quantum professionals in the world. But you can prove me wrong, but I will make that claim. So this is where we are today, and we have a lot of nice people coming this week to present and talk about quantum. First off, I'm very happy to introduce our keynote speakers. We have Anna Graselina, we have Nathan Lacroix, and we have Harry Buterman presenting their work during this week. And I think they all encapsulate sort of the status of the field of superconducting qubits, which is that we are now having multiple labs around the world that really do real quantum error correction. Also, they're done not just on small demos, but on real quantum systems with, let's say, 100 plus qubits. I say experiments with that is common. Okay, it's not every lab that has it, but I would say when you see a paper on arXiv with 100 qubits, you're not surprised to see that anymore. So I think that is cool. We are also at the stage where I would say materials and fabrication and all the engineering efforts that goes into building these systems are really taking a next step beyond, let's say, what we saw maybe 5 years ago, where it was really driven by academic efforts. Now, I would say it's driven by both academia and very large industry efforts. And really, I think those sort of states or the status update of the field is really also addressed by all the other invited speakers that we have this week. And I think what is very interesting, if you sort of compare this year's edition of SQA to the 2 previous editions, which was 2 years ago and 3 years ago, is I would say we have more focus on algorithms, meaning people are actually starting to do things with superconducting qubits. I think that's exciting. And there's a lot of focus on scaling, like how do we actually take these systems from small demonstrators to more useful full stack systems. So these are sort of some of the themes that I think stands out this year compared to previous years. What we will more specifically do, and here I will show the program for today in a somewhat detail. So once I'm done talking here, we will have a keynote, the first keynote of the week from Nathan Lacroix from Google. And then we will have a scientific session on quantum error correction to really highlight some of the efforts in the field, both experimentally and theoretically. Then we will step outside of this room into the area here, and we will have a welcome reception, which is supported by quantum machines and QTech. And then at the very end of the day, we will come back in here, and we will have a talk with David DiVincenzo and a few others. And you can really ask them anything. So if you really want to know what is David's favorite gauge transformation, now is the time to ask him. Then I will not go through the rest of the days in so much detail today. I will do that, of course, the other days. But we will tomorrow have a full day with talks and poster sessions. And at the end of tomorrow, we will have excursion to the ecosystem, generally speaking. Same on day number 3, which is Wednesday. We will have scientific session, poster sessions. And at the end of Wednesday, we will have a dinner in, as I said, the new church, which is somewhat old. And then finally, last day of the session, last day session of the conference is on Thursday. And I want to specifically highlight this, in case you missed it on the website, is that at the end of Thursday, we have a poster prize award announcement, meaning that 3 out of all the posters will get a Best Poster Award. So stay until the end to see who wins the poster prize. A few practical points. Our keynotes are 45 minutes plus questions. Invited talks are 25 minutes plus questions. And contributed talks are 12 minutes plus questions. Just to give you a rough idea, but we will not keep it super rigorous, but at the same time, don't go over time. If you want to see more details about all the talks, the program is on the website. And if you scan this QR code, you will get to the page where you can see all the abstracts. It's a nice online system, and you can just sort after session, sort based on your favorite topics, and you can find all the abstracts. That was sort of on the scientific program. A few more practical things that I need to say before we really get started. We are in Delft. Delft is a small city. Everything is walkable or bikeable. I know so many of you have reserved their bike through the reservation system here, so you can bike around. But for people that are not used to be in the Netherlands, bikes generally do not brake when they see pedestrian. So if you are walking and there's a bike, it's good to let the bike pass. This is a map of Delft. We are here in this building, in the theater. Right next door is the cinema, and some of the workshops that you're attending is in the cinema right next door. The church is up here. Google says it takes 7 minutes to walk there. I believe them. The best way is really just to go out of the main entrance to the canal. Then you follow the canal, then there's a square, you just keep going straight, and then you're there. For the ecosystem tours, you sort of cross the big bridge here, and then all of Delft is down here. But we will also have volunteers to show you around, so hopefully you should not get lost. Other practical info that is important is you have these badges. Please wear them at all time. It's not because we want to like play police, but we are downtown in Delft. In principle, everybody could walk into here. And just to keep a little bit of control, please wear them. It will just make it easy for us to see you're part of the conference. We can let you in, and it's easy. So also, for the workshops and side events such as the excursions, in principle, you can still sign up for them. I think most of you have. But if I look at the numbers, there's maybe a good handful of you that did not. So if you did not sign up for the workshops, you can still do it. And just again, mentioned before, but the workshops are at the cinema, which is right over there. And as I said, volunteers will guide you there. Again, if you did not sign up, you can now scan this QR code, or you can go to this link, and you can sign up for the workshops, etc. Now, almost at the end of the practical session, I mentioned the poster session. The poster session will be set up right here on the stage once we get to that in tomorrow. So that will go hopefully very smooth. So once we are done with the session, a couple of volunteers will boom, 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 set up the poster, what do you call them? The poster frames, good, yes. Poster frames, and then you just go up and hang your poster if you have a poster. Outside here, which is right over there, there is a terrace from the local restaurant Moods, and you are free to use that at all time during the conference. If you take a drink here and you want to go outside and drink it, you can just go to the terrace. But if you bring any drinks, take them back into the venue, please. Also, if you want to eat dinner, for example, tonight where we don't have a planned dinner in the conference, you can also go to Moods, and they will have a special SQA dinner menu. I don't know what it is. I don't know if it's good, but it's special SQA, so it's at least something. Then, almost at the end of my practical information, so Wi-Fi, if you did not figure it out, you go to the Theater de Veste Wi-Fi, and this is the Wi-Fi password. If you are in doubt of anything, this red table here is the info desk, and there will be people sitting there all day in case you have questions, if you get lost, if anything. And in principle, all the information that I just mentioned is also available in the conference guide. There's a link on our homepage, and you can scan this QR code, and then you should get all the information. And then again, finally, let's thank one more time to all our supporters. And with that, I want to get started with our first keynote session. So the first keynote speaker is, as I mentioned before, Nathan Lacroix, who did his studies at ETH Zurich, where he got a PhD in the group of Andreas Wallraff. Towards the end of his PhD, he also did an internship in Google, and now he's a research scientist at Google Quantum AI. And today he will present his work on scaling and logic in the color code performed on a superconducting qubit processor. So with that, welcome, Nathan.
Okay, thank you for the kind introduction. I'm very happy to be here, and it's a great honor to open this conference on superconducting qubits and algorithms. And today will be mostly about quantum error correction, and I'm very excited to be here to tell you about some of the latest results that we achieved at Google that is about demonstrating scaling and logic in the color code on our Willow processor. So before I start with this, because it's the first talk, I want to remind ourselves, sometimes it's good to do this, why we're doing what we're doing. And at Google, we really want to build a useful quantum computer. And we know that many practical applications of quantum computers requires programs that have billions of operations, if not more. So to successfully execute those, we need to make sure that the error of each gate is way smaller than that, so on the order of 10 to the minus 10 per gate. And yet currently, we made a lot of progress, but the operations that we can implement on the physical devices that we build have error probabilities of about 1 in 1,000. So quantum error correction is really what allows you to bridge this gap. It's 7 orders of magnitude. It's like comparing the speed of a snail to the one of a bullet. It's like very far away. But what's exciting is that we're starting to get there. So I want to briefly remind you what are the 2 key components of error correction. The first main concept is redundancy. One way of achieving redundancy is to use many physical qubits, so the one that we can build, that have somewhat high error rates, and put them together to encode fewer logical qubits. And these, hopefully, have lower errors. The second big component is a method to infer errors. So the way that I will be speaking about it here is I will use stabilizer measurements. The idea there is that an auxiliary qubit, shown here in blue, will measure the parity of the neighboring data qubits, shown in yellow, and ask whether the parity is even or odd. And we will encode the system such that we expect it to always be even. So we do a sequence of operations, and later today there will even be a talk about how maybe this can be done more efficiently. And the result is 0 if the parity was even. And if there's an additional error that happens on, or a bit flip on one of these data qubits, then the measurement outcome of these auxiliary qubit will be 1. And so you know that you're not in an even state and that there has been an error. Of course, this comes with caveats. So the redundancy means you need a lot more qubits, or at least you need some more qubits. How much more? We're going to discuss this today and later in this conference. The second aspect is that this whole scheme works only if all the operations on the physical qubits are already below a critical error threshold. And this is also important because it sets some stringent requirements on what we can do with what we can fabricate. So this is, if you explain to your grandma, that's how I would explain error correction. But of course, if you try to do it in practice, everyone knows it's a lot more complicated. There's so many choices you can make. For example, the platform. Here we're all convinced that superconducting circuits is a good avenue, so we won't discuss this. But even if you fix this, there's still a lot of other aspects that you can choose. What encoding do you use? Do you use continuous variable encodings? Do you use discrete variables encodings? Later this week, we will also discuss some of this. Do you use the transmon qubits, or do you use fluxonium qubits? What gate implementation do you use? What decoder do you use? What error-correcting code do you use? And all of these choices offer trade-offs between qubit quality, efficiency, what connectivity. Later there will also be a talk about connectivity of superconducting circuits. We're going to speak about scalability. So there's so many aspects that matter. And here I want to tell you about how at Google we also want to explore this trade space. And I will focus on the choice of the error-correcting code. Most of you know that at Google, we focus a lot on the surface code. And there's a reason for it. It's pretty good. So it has a very high error threshold of about 1%. That means that it has compared to its peers, it has the lowest requirement on the physical operations, on the performance of the physical qubits. And so it also has a very convenient connectivity requirement, which means that it only needs to talk to 4 nearest neighbors, and there's well-known decoding technique to infer the errors that happen on it. But as we're making better and better devices, we suddenly start to realize that maybe we don't need to have our choice driven only by how hard it is to make an operation. maybe we can rethink this and think about other codes where maybe it's a bit harder to get there, the threshold is a bit lower, but it offers other advantages. And this is what I really want you to remember from this. We're now at a stage where we can look also at other codes, especially for superconducting circuits. This is where the color code comes in, because it has a lower threshold, slightly lower. It's, by the way, it keeps increasing as the decoders get better. But for now, the decoding is still harder than for the surface code. But it has some advantages. At a fixed distance, it uses less physical qubits per logical qubit that you build. We'll come back to that. It's also, very importantly, easier to implement logic, what we ultimately want to do, with a color code than with a surface code. And recently, we also discovered that it's possible to implement the color code with nearest neighbor connectivity. And personally, I think that this has been a big game changer, because before we were really also not looking at the color code for that reason. So there's been a lot of experimental work on the color code, but mostly on trapped ions, where they've done some distance 3 memory experiments. They've also demonstrated logical operations and even logical computations. Same with neutral atoms. They have already looked at making some computations with the color code. But where are we with superconducting circuits? So far, there's not much. And this is what we wanted to change. Also, if you look at the experiments that are already out there, none of them show that there's any suppression of errors when you increase the distance. So this is the first challenge that we wanted to solve. So here's an overview of the result that I want to present to you. We have 4 main results. The first one discusses that we can operate a color code qubit below its critical noise threshold. That means that if we increase the distance from 3 to 5, we can decrease the logical errors. The second aspect is that we can implement logic. So I will speak to you about how we can implement Clifford gates on a distance 3 color code and benchmark them using logical randomized benchmarking. The third point is that we managed to inject magic states, which is an important resource for quantum computation, into a distance 3 logical qubit. And last, that we can take multiple of these qubits and make them interact using lattice surgery, which is a fault-tolerant way of making operations between different logical qubits. So let's get started. We use a color code that is implemented on a hexagonal tile that you see here, and each tile that you see has an X stabilizer and a Z stabilizer that has supports on all its vertices. The circuit that we use to infer the errors, the stabilizer measurement or syndrome extraction circuit, is called the superdense circuit. It has 2 auxiliary qubits per tile, so they're shown here in red for this red tile. And one of the features of this is that it can measure the X and the Z stabilizer at the same time. I will tell you more about how this works. And one important aspect, as I was saying, is that it can be implemented on a grid of qubits that has a square connectivity. And for an equal distance, this uses 25% less qubit than the surface code. So just one intuition about how the circuit works. It inspires itself from superdense coding, which is a technique where you can use a bell pair to encode 2 classical bits, one in the parity of the bell pair and one in the phase of the bell pair. And those 2 are orthogonal. So you can use this property to create a bell pair among the 2 auxiliary qubits, and then each of those will make C-naughts with their neighboring data qubits. And in the first part, they will do a C-naught that will check whether any of the data qubits had a bit flip. And if so, it will flip the parity of the bell state. And it doesn't matter from which side it happens. This is where the idea of the shared quantum resource allows to have this 4-fold connectivity, because each auxiliary qubit doesn't need to interact with all of the data qubits. Then once this is done, it measures the X-type stabilizers and checks for phase flips by flipping the phase of the bell pair. And then the bell pair is disentangled, and we measure whether there has been a bit flip and a phase flip. So this is how it works. The first experiment that we set up to do is comparing 3 distance 3 logical qubits to 1 distance 5 logical qubit and check whether the performance of the larger one is better than the one of the small one. So the experiment here is very simple. You prepare your logical qubit, you do n rounds of syndrome extractions, and then you measure your logical qubit. You compare the decoded state to the target that you had, so to the initial one that you intended to prepare, and you repeat this many times. And then from this, you can calculate the logical error probability, and you can do this for various number of cycles. So if you do this, this is the type of plot that you get, and you can, so here we have the number of cycles, we have the logical error, we have the mean of the distance 3, and then we have the distance 5, and you can see that the error rates the error rate of the distance 5 qubit is lower than the mean of the distance 3 qubit. So that's great, because it means that we're able to suppress errors by increasing the distance, and the error suppression factor is about 1.5 or 1.6. So the first thing that people ask me when I present this is, well, is it better or is it worse than the surface code? Well, it's complicated, but let's look at it. So in terms of pure qubit efficiency, so how many qubits do you need? Currently, on the Willow device, the surface code requires has a error suppression factor 2.2, and the color code is around 1.6. So it's larger for the surface code. But that's not ultimately what we think will matter, because what will matter is how many qubits do you need to have your logical error rate at 10 to the minus 10. And there, the story is a bit different, because since you need less qubits at a given distance for the color code, you can use a larger distance for the color code for the same number of qubits, if you have a fixed number of qubits at your disposition. So currently, we still see so the data that you see on the right-hand side is the logical error per cycle versus the number of physical qubits. And the experiment that I was just showing you is up here in yellow, and the blue one is the equivalent experiment on the surface code. Those are done in 2 slightly different settings, but you can see that clearly to go to 10 to the minus 10, you will need a lot of qubits, and you will need about 2 times more for the color code. But if we are able to slightly reduce the errors that we currently have, and we think this is really within reasonable reach, the simulations indicate that a factor 2 or 2 to 4 improvement would make the color code equally or even a bit more qubit efficient in a memory setting than the surface code. So those are those 2 lines that you see here. This is for a factor 2 improvement, and this is for a factor 4 improvement. So it's really exciting, because it shows that maybe now or soon we won't need to limit us just to the surface code, because it will use less qubits. In fact, if you consider logic, it may be the case that this break-even point will occur even sooner, because as I was telling you, the color code can do logic more efficiently. So it's important to also already now build some practical experience with logic, and this is what I'm going to speak about for the rest of this talk. But we also want to have some detailed resource estimation studies, and this we hope that the community is also interested in this, to compare really what it will take to run algorithms with a surface code and with a color code. So let's speak now about logic. The requirements for arbitrary logic is to have a universal gate set. One way of constructing this is to have the single qubit Clifford gates, which consists of the Hadamard, the phase gate, poly gates, and combination of these. One non-Clifford gate, for example, the T gate on a single qubit, and then one entangling gate, for example, a C0. And if you ask any experimentalist how would you want to implement your logic gate? Most of them will answer that they want as many as possible transversal gates. A transversal gate is a gate that if you want to implement it on your logical qubit, you just need to apply a single qubit gate on each of your physical qubits, of your physical data qubits. And this has some main advantages, because it's automatically fault tolerant, so because the errors are contained, and also it's very fast. It just requires one physical gate layer. And if you compare the surface code and the color code, the surface code cannot implement any of, or cannot implement the Hadamard gate nor the phase gate transversely, while the color code can. So that's very interesting. And we decided that we wanted to benchmark this. So to do this, we need to start using some characterization technique that are on the logical qubit. And here we decided to use logical randomized benchmarking. Probably most of you are familiar with how this works. You generate some random Clifford circuits, and you interleave each of the QEC circuits or each of the syndrome extraction rounds with a Clifford circuit, and you compare it to a circuit where you do not have any of these Clifford operations or any of these logical gates. And so what we find is the following, namely that like if you just idle compared to if you add additional gates in between, it makes practically no difference. So the additional error that you get per Clifford gate is about 10 times smaller than the error itself of idling. So idling is really the hard part for us, and the transversal gates are very convenient. That's what we learned from this. But the T-gate is more complicated. The T-gate cannot be implemented transversely in the color code or in the surface code, and there's a few different circuits to realize, that we think will be used to realize them. The traditional one is to inject what is called a magic state. So this is a resource state, and you prepare it in a non-fault tolerant way. And it cannot be prepared in a fault tolerant way. And then you take many of these and you input it in the distillation circuit in the same way that like distillation of alcohol takes some lower concentration and yields some higher concentration. Here what you're going to do is that you will have some purity and you will, in the beginning, so you will have some infidelity here, and the infidelity here will be a lot lower. So the purity will be a lot higher, about like 1,000 times for, it depends on the circuit, but that's the second big step. And the third step is to do a gate teleportation. So you need to do all this to do a single T-gate. And this is why we think that this might be also the most critical part of quantum computing in practice, because it will require a lot of resources just to do a single T-gate. There's some important aspects that matter here. So this scheme can be applied to any error correction code, so it can apply to the color code, to the surface code, to other codes. And the fidelity of the input state here matters because you might have to distill several times if your fidelity is not high enough. So we were interested in seeing how high is the fidelity of our state that we can prepare here. Also, post-selection in this case is acceptable because you can, in principle, try this part of the circuit as many times as you want before actually applying it to your actual logical qubit that you care about, since this is actually just an auxiliary qubit. But it doesn't come for free because, of course, like if you have a higher post-selection rate, it means that you need to wait for longer in between your gates. So that matters, but you can actually do it. Another way of doing the T-gates and how to do them specifically on the surface code that actually use less resources is to inject a magic state in a color code and then grow its distance and progressively deform it to a surface code. And by doing this, so this is based on some work from Craig Gitney, it turns out that you can use a lot less resources than was thought initially. So here you see that the color code might be important even for surface code computation. What we lost here is the generality. This doesn't work for any code or for all codes. So now let's have a look about how we can implement this magic state injection. So this first step here that we looked at. The idea is that you want to prepare a magic state on a physical qubit. So this one here is the data qubit. In yellow, you have the data qubits. And you inject your state that you want to prepare on this qubit using arbitrary single qubit rotations. And you inject it from the physical qubit into the logical qubit. And to do this, you prepare the data qubits, the other 6, pairwise into Bell states. And this ensures that the logical operator grows deterministically from the physical qubit to the logical qubit. This is, of course, important to make sure that you retain the quantum information that you intended to inject. Then you do one round of error correction, and then you do tomography, logical state tomography, and you calculate the fidelity of the state that you prepared compared to the one that you were initially interested in. Here's the experimental results. So we prepared 3 different magic states. You can see them represented here on the block sphere of the logical qubit. And we vary the rejected data fraction, so how much we post-select. And you can see that the fidelity of the magic state varies between about 5% and 10 to the minus 3 here. So this means that we're able to really prepare a high fidelity magic state because it's well beyond what is needed to actually perform distillation. That fidelity requirement is about in the high 80%. And it also means that you can yes, so you won't need too many rounds of distillation because your fidelity or input fidelity is already high enough. So this performance we were really excited about it because it's actually quite higher than the other work on superconducting circuits that are doing magic state injection on the surface code. So there we're also very interested to see that this performs really, really well. And once we finished with this, we decided to move on to lattice surgery. So lattice surgery uses local operation to perform logical parity measurements. So a sequence of these lattice surgery operations enable a logical C0. So for example, to do a C0, you need 3 qubits, one control qubit, 1 target qubit, and 1 auxiliary qubit here in the middle. And you do a parity measurement in the X basis, and then a logical parity measurement in the Z basis, and then you read out your ancilla, your auxiliary qubit. So what we really see here is that we can look at one of these operations and try to implement it between 2 distant 3 logical qubits. And this will really teach us a bit about what type of errors we can see in this scenario. So the way that we decided to characterize this is to characterize one logical XX measurement by using state teleportation. So the scheme is that follows. You have 2 distant 3 logical qubits, and you prepare an arbitrary state, or in our case, it will be only a poly state on this qubit L1. Then you do the parity measurement, and then you do some additional frame updates, and you measure both qubits in so the first qubit in the Z basis, and the second one you do a logical tomography, and after doing the polyframe updates, it turns out that you should have exactly the same state as the one that was prepared here. So by then doing some tomography on this second logical qubit, you can calculate the fidelity of the state with respect to what you had initially intended to prepare on your first qubit. So the question that we're asking is how close is the final state on L2 to the initial state that we intended to prepare on L1. So here's how the protocol looks in more detail for distant 3 color codes. We initialize the logical qubits independently. And then after we prepare L1 in one arbitrary state, and then we do this merging operation. This is the step of the parity in the X basis. And the way this works is that you measure the merging stabilizers only in the X basis. So those are the 2 that are here hashed. And you measure this for 3 rounds. So you do 3 rounds of error correction. And once you've done this for 3 rounds, the reason why we do 3 is that the distance is 3, and you want to make sure that you have enough cycles so that you're not perturbed by any measurement errors. And then you read out this line in the middle. And finally, so this is called the split part of the logical lattice surgery operation, and then you measure both of these. So the first one you measure in the Z basis, and you do the tomography on the second one. Just as an information, so for now we do this polyframe update in post-processing, so we don't do it in real time. But ultimately, if we want to implement T-gate, sometimes some of these polyframe updates will be will have to be done in real time. So here are the results. We decide to teleport the state 0 plus minus state from L1 to L2. And the next step that we will do is to decode the expectation values. Wait, let me walk through all of this, I think, before the image arrives. OK, there we go. So we prepare. So let's take an example of the 0 state. We prepare the 0 state, and then we measure it in all 3 possible bases. And we see that the expectation value of the logical observable is close to 1, only in the case so in the logical 0 state, we see that the logical value of the Z observable is close to 1. So this is what you would expect. What you would expect to be a perfect response is a dashed line here. What we actually measure is a colored line, and we have some poly simulations that show this black wireframe. So you see that we have a relatively good agreement with the ideal expectations, but also very good once we take into account the simulation of the errors that happen on our device. And the state fidelities that we reach are in the high 80s up to the low 90s. And it's interesting to say that also on another platform, they were able, so with trapped ions, they were able to achieve even higher fidelities of 93 to 95%. So those are the fidelities. So we're really excited because that means that for the first time we can actually take logical qubits and start doing, maybe even in the near future, some small algorithm on these logical qubits. So it's a really exciting period. I just want to give you a brief summary of what we've discussed so far. So in this work, we showed you the first experimental realization of color codes using superconducting qubits. And that is operated below the critical noise threshold. We also did some logical randomized benchmarking and seen that the error of the transversal gate is relatively small compared to the error per cycle. Additionally, we were able to demonstrate magic state injection with fidelities up to 3 nines, and we teleported states via lattice surgery with 90% fidelity. So it's really exciting. But it's not all. There's still a lot of things to do. So let me tell you about some of the next steps and where we think that also it will help for the community to get engaged into the color code. The first thing is that we need to develop some next generation decoders for high accuracy decoding in real time. Currently, the decoding of the color code takes a lot longer than the one of the surface code. And if we want to be able to perform some computation in real time, we need the color code decoders to catch up. That's one big workhorse. The second one is to develop strategies for dealing with dropouts. What if one qubit just on your chip doesn't work? How do you deal with this? There are known ways to deal with this in the surface code, but we don't know yet how it would work on the color code. So understanding this would also be crucial from a practical perspective. Then, of course, there's a couple of next steps, but we want to demonstrate the suppression of transversal gates by increasing the code distance. So far, we only demonstrated it on the memory, but we also want to show that as you increase the distance, your logical error rate of the gates that you perform, for example, the transversal gate, also goes down. Because ultimately, we want to do computation, and computation is done with gates. The next step is, or another important aspect, is to distill or cultivate magic states using the color code. So this is what I was telling you in the magic state injection. We basically did the first step. We want to do the other step so that we can realize one full T-gate. And another learning that we've made is that as our qubits get better and better, we might want to even explore other codes. Because what we've learned so far is the decision about using the color code, or sorry, the surface code was probably made when I was in primary school. And it turns out a lot of things can happen between this and now. So with this, I thank you very much for your attention, and I'm ready to take any questions.
have good times for question, and the way this works is if you have a question, raise your hand, and I will throw this. It's very soft, so don't be scared, but I will throw this to you.
Down there.
Right, yes.
Wow.
Yeah, I think it works. Thanks for the great talk. I have a question specifically for this logical randomized benchmarking. You say that the trace when you're done to Cliffords is idling. So do you mean that you're actually leaving the amount of time that it takes the Clifford on the other trace, or do you just continuously do the cycles? Does it make any difference either way?
Yeah, that's a great question, and there's a lot of details that can go into this. But the main point is what I mean by idling means that I do repeated cycles of error correction. In that case, we don't even wait for the time that it takes to do one gate. There's also some level of complexity because in principle when you do Cliffords, as long as you do Clifford circuit, you can in principle propagate them through the circuit. So it's also possible to even take into account your Clifford operation by changing the operations on the qubits nearby. So for example, if you do a Hadamard and there's already some data qubits on which you do a Hadamard, then like this one can cancel out. So there's a lot of details and we're still learning about what is the best way to actually demonstrate it, because in practice it's not clear how you would, or at least we don't have so much experience with it. But so far what I can tell you is that we're not waiting for idle. So we're just doing like a memory experiment like we do it traditionally, just with the same number of cycles.
Thank you.
Yeah, hi, thanks. Amazing progress. I gather that the experiments you showed today were on Willow. Do you foresee that, if you decide color code is the best code or you find another code, will that also go along with a rework of the hardware? That is, there will be a re-optimization of the actual physical qubit layout schemes and couplers to, get it closer to the native layout that's implied by these codes? Yeah,
that's a very good question. It's one of the main reasons why we also did this work was to test our hardware, to see how well can we perform something that has been really optimized for the surface code and now try to implement another code with it. And we definitely had some surprises. One that I can maybe give you, because we have some time, is that, let me see if I... Okay, I don't see it here. But the point that I wanted to make is that, so for the color code, it turns out that for the surface code, the way we have arranged our readout lines, all the data qubits are on the same readout line. But for the color code, it turns out we would have a slightly different arrangement, and we would have on the same readout line some auxiliary qubits and some data qubits. And there you can have some dephasing from one qubit to the neighbor. And so these kind of things matter in hardware. So it's possible that we do some adjustment if we were to decide that we want to use another code, but we also want to understand what is the trade-off between making something generic and something very specific. So we're not yet set on that kind of things, but mostly we want to understand what are the choices that we are making and how is this somehow overfitting to some specific instance. So this is still a bit open for us at the moment.
We still have a good time for questions, so yes, over there. Okay.
There's a question down there.
Yes.
Thank you very much for the really nice talk. I wanted to pick up on your point about the need for, kind of higher accuracy, more efficient decoders. I was wondering if you tried any of the kind of, more efficient graph-based color code decoders on your results, on your data, and if it had a significant result, if say, being below threshold required one of those the really high accuracy neural network decoder.
Mm-hmm. So maybe I can, let's see if I can show, so we tried a bunch of decoders. So, so these are, we tried 5 different techniques, so the first one, because there's 2 things that are important, the decoder itself and the error model that you give to it to try to infer where the errors happened. The first method here is the most vanilla one. It's one that we currently know we can use in real time in principle. We haven't demonstrated it. And we use a prior that says all the qubits should be the same. Then, and you actually see that here, the distance 5 is actually a bit worse than the distance 3. So as you go down here, we do more and more elaborate, we have more and more elaborate decoding strategies. And you see that it gets better and better. So the second one is the same, the Chromobius decoder. So the same decoder, but a better prior, a prior that uses reinforcement learning. And there you see that we're getting close to the break-even, but it's still not as good. Then the third one here is actually using a more advanced decoder that is probably not scalable to very large distances, or it's at least relatively slow. I think it takes about a millisecond per shot per cycle, so that's quite a bit larger than our cycle time. So we don't think that currently this implementation would make it in real time, but it's possible that it can be improved to be run in real time. And there you see that we already get to an error suppression factor that is larger than 1. And if you then use the most optimized method that we currently know, this is this neural network decoder that is fine-tuned on experimental data, and this is where we get the best results. But it's actually not so much better than this maximum likelihood decoder, most likely error decoder, which is not maximum likelihood, most likely error decoder with iterative edge reweighting. So we think that we have, in principle, good decoders. They just need to be faster.
Thank you.
Good. We have maybe 1 or 2 more questions, if anybody is. Good. In the back, all the way up there, yes. Okay. Can you hold this?
Oh, good aim.
Wes, thank you for a very pleasant talk. It was great following along. In regards to your last point, it's really cool to see something that's not the Cephas code and something that goes a little bit further towards the color code, and even further than that, you say that we should look into multiple codes in the future. The quantum error correction community is doing stuff like transversal non-Cliffords and stuff like that with changing Clifford hierarchies. Like, there's a lot of theoretical work that's been put out the last 5 years, and we're nowhere near that at a level of hardware. I would like to ask, do you have any idea what the next step in the quantum error correction codes that we're going to look at is going to look like? Something beyond color code.
So I think that the answer will very much depend on who you ask. If you ask me, it will probably stay something that is that doesn't ask for too high requirements in terms of connectivity, because if you start doing this, it gets really complicated on the fabrication side. You might also spread correlated errors further, and all these things really matter currently at the stage that we're at. Maybe if it turns out it's easier to do that specific technology. So actually, maybe the answer is depending on which technology gets a much better, let's say, a jump, it will enable different things. If we find a way to really make long-scale connectivities between different qubits on the chip, then maybe looking at LDPC codes will start getting, or a good LDPC code will be interesting, but it's very hard to tell at the moment. I guess it will depend a bit. Currently, the approach that I see is working well, is trying to improve everything and then see what are the codes that work with the current error rates that we have.
Thank you very much.
Great. If there's a final question, we could take that.
Down there?
Yeah, down there. Yes, I need the mic.
Hello. Thank you very much for your presentation. My question coming from a different perspective, quantum communications. So I'm a newcomer here, but I have a strong interest or a curiosity regarding the quantum logical qubits. do you see that the handling or the manipulation of the logical qubits straightforward, or do you see more challenging than the physical qubits? I'm thinking about entangling even quantum logical qubits.
I can tell you it's definitely more challenging.
Okay.
Dealing with, you're basically still dealing with many physical qubits, and you can never really, or at least currently, it doesn't work yet at a stage where you can fully ignore the physical qubits. We try to build our tools such that we can one day get there, but one important aspect that I think would also be very interesting to hear more about during this conference is time stability of all of the physical components and of the electrical components of the control systems. Like, all these things really matter, and they might matter differently for the different physical qubits. And so if all of that is really stable, then manipulating the logical qubits is very easy. But you need to get to a stage where really your physical qubits are stable. And we also learn a lot of things by doing these different logical circuits, because the types of errors that you see may be different. For example, in the lattice surgery, time-like errors start to be more limiting. So for example, if you do only one round of syndrome extraction when you merge two logical qubits, you will have different types of errors than when you do a memory experiment where you are really more limited by space or space-time-like errors. So that also matters. So I hope that answers your question. And I just want to point out that this work was done by a large team of people, so the whole quantum AI team, also my close collaborators, Alexandre Bourassa and Craig Gidney and Kevin Satzinger. And if you're interested in joining the team, we're also hiring, so feel free to come and talk to me later during this conference. Thank you very much.
And as a thank you to all the speakers, so you will see that all the way during the week. The speaker will get a Delft Blue special SQA design and a piece of chocolate.
Perfect. Thank you very much.
For the next session, we will hear about more quantum error correction, and to present that, I will give the word to Alexandra Occhiani.
Hi everyone. So it's a pleasure to be here. I'm Alessandro Ciani from Forschungszentrum Jülich, and let me start this session first by thanking the organizers for setting up this amazing conference here in Delft. For me personally, it's also a pleasure to be back because I lived in Delft for 2 years. And we're also blessed by beautiful weather, and Delft is really beautiful today. So let us start. The first talk is given by Ophelia Crawford from Liver Lane, and the title is "To Reset or Not to Reset? That is the Question." Yes.
Great. Hi. Thank you very much for having me. It's lovely to be here. So today I'm going to talk about different schemes for mid-circuit reset and the effects they have on quantum error correction protocols. As we heard a lot about in the previous talk, in quantum error correction, we use multiple physical qubits to represent a single logical qubit, thereby introducing redundancy into the system and providing some protection against errors. In this talk, I'm going to focus on what we've heard is a popular code, the rotated planar surface code. This is particularly well suited for superconducting hardware due to its planar degree 4 connectivity needs. We have two types of qubits, physical qubits that we use to represent the surface code. The data qubits shown in yellow, which encodes the logical information in the qubits, and the auxiliary qubits shown in black, which we use to measure stabilizers across the data qubits to detect errors. In order to measure those stabilizers, we use what's known as a syndrome extraction circuit, and this has typically the structure. We first of all reset the auxiliary qubit. Then we perform 2-qubit gates between the auxiliary qubit and the data qubits. And finally, we measure the auxiliary qubit. And we repeat this process many times to continue detecting errors and protecting our logical qubit. So this kind of syndrome extraction scheme is the standard textbook way of measuring our stabilizers, where we reset the auxiliary qubit every time we perform syndrome extraction, every round, using an unconditional reset. However, performing high-fidelity, fast, mid-circuit unconditional resets is difficult, and therefore it can be useful to think about different reset schemes. For example, we could perform a conditional reset, where we use the measurement result from the previous round of syndrome extraction to conditionally apply a 1-qubit X gate to the auxiliary qubit to return it, or hopefully return it, to the 0 state. What we could also do is actually have no reset at all, use the no reset scheme. And this is actually equivalent to the conditional reset scheme. Instead of applying the conditional X gate on the auxiliary qubit itself, we can instead keep track of it in software. And what this means is I'm not going to consider the conditional reset scheme any further, because it's equivalent to the no reset scheme, but requires more 1-qubit gates. Before going forwards, it will be useful for us to have a look at the structure of the decoding graphs in the two schemes, the unconditional reset scheme and the reset scheme. And so here I'm showing a segment of the decoding graph just for a single stabilizer. The decoding graph is what we pass to the decoder so it can attempt to understand the errors that have happened on the device and hopefully tell us how to correct for them. So on the left here, I have the structure of the decoding graph in the unconditional reset case. These circles or nodes are made up of combinations of measurement outcomes on a particular auxiliary qubit in neighboring rounds. And the edges represent errors that will flip the detectors, those combinations of measurements, on either sides of the edge. So what we can see here is that a measurement error in the unconditional reset case will flip the two detectors on either side in neighboring rounds. However, in the no reset case, we have a different structure of decoding graph. And as discussed in this paper, we define detectors slightly differently in the no reset case. We take measurements that are 2 rounds apart. And what this means is we get these additional edges that go between detectors 2 rounds apart due to our measurement errors. So yeah, as I'm sure you're aware, recently across all different hardware types, all different kind of quantum error correction codes, there have been a huge range of quantum error correction experiments. I'm just picking out a few examples, superconducting experiments on the surface codes recently that use both, in some cases, the unconditional reset scheme and in some cases, the no reset scheme. And these works inspired us to look in more detail at the effect of the different schemes on quantum error correction, and in particular to look forwards to their effect on logical operations and potentially kind of fault-tolerant calculations in the future. So to look at that, we examined both quantum memory and also logic in the context of the surface code. And much like in the previous talk with the color code, the popular way to perform logic with the surface code in superconducting qubits is to use lattice surgery. To start with quantum memory, I have a schematic diagram on the left-hand side here with a single logical qubit in the plane and then moving through time as we go upwards. And a representation of a logical error is shown here as this black horizontal line. So if we have a string of errors across the code, we will have a logical error. And we can decrease that probability of a logical error by increasing the size of the patch. This increases the distance, which is the smallest number of errors required in order to have a logical error. In lattice surgery, we have an additional type of logical error. So This is showing 2 logical qubits on the sides, and then, as we saw in the previous talk, we merge those 2 logical qubits together and perform syndrome extraction for some number of rounds. And we can have a logical error in the lattice surgery case running vertically, which is a string of physical measurement errors in every round of syndrome extraction. So what this means is that the distance of this part of a lattice surgery experiment is controlled by the number of rounds of syndrome extraction we perform. We, in our work, didn't actually look at a full lattice surgery operation, but used the stability experiment, which is a proxy for this particular, the kind of merge stage part of a lattice surgery operation, and behaves in a similar way, where we can have logical errors that run from top to bottom, and the number of rounds of syndrome extraction we perform controls the distance of the experiment. So I've introduced the 2 reset schemes we would like to consider, and also the error correction experiments, memory and stability, that we would like to study these schemes in the context of. And I'm now going to present some results, both some theoretical results and also some simulation results. So firstly, as we saw, the key difference between the unconditional reset and the no reset schemes is the addition of these edges in the decoding graph that go between detectors 2 rounds apart. So what has previously been mentioned in the literature, and our work is consistent with this, is that we don't expect the difference between the unconditional reset scheme and the no reset scheme to be significant in the context of quantum memory. Because in that case, logical errors run horizontally, but the key difference in the graphs is vertical. However, in stability, where we do have these logical errors that run from top to bottom, what we observe is that the distance of a stability experiment, if we use the no reset scheme, is actually halved relative to the unconditional reset scheme, because we have these edges that go between detectors 2 rounds apart. So what that means is, in order to achieve the same distance of a stability experiment, and therefore a lattice surgery operation in the no reset scheme, we'd have to perform twice as many rounds of syndrome extraction. To supplement and complement our theoretical results, and also to understand the impact of them in practice, we also performed some simulations of quantum memory and stability using a superconducting inspired noise model, simulated using STIM, and decoded using the minimum weight perfect matching decoder pi matching. Here I'm showing the quantum memory results, which are consistent with what's been previously observed in the literature and our theoretical observations. So on the x-axis, I have the physical error parameter, and on the y-axis, the logical error probability. And we're showing for different distances the performance in the unconditional reset scheme in the solid lines, and the no reset scheme in the dashed lines. And we see the performance is very similar. The no reset scheme slightly outperforms the unconditional reset scheme. This is because when you're applying resets, the data qubits are accumulating additional idle noise. Moving to stability, where, recall, we have this distance halving effect in the no reset case. So here I'm showing the number of quantum error correction rounds on the x-axis and the logical error probability on the y, with the different colors representing different physical error probabilities ranging from 10 to the minus 2 to 10 to the minus 3. Again, the solid line is the unconditional reset case, and the dashed line the reset case. And here we can see there's quite a difference in performance for a fixed number of syndrome extraction rounds. The unconditional reset scheme, at least in the lower physical error probability cases, is significantly outperforming the no reset scheme. However, this isn't completely fair. As I mentioned in the memory case, resets take time. So really what we'd like to understand is, for fixed performance, how does the time taken to achieve that performance compare with the unconditional reset scheme and the no reset scheme? And this is what we're showing here. So if we're on that dashed red line, then the 2 schemes achieve the same logical performance in the same length of time. If we're above that line, then the no reset scheme actually outperforms the unconditional reset scheme. If we're below that line, the unconditional reset scheme outperforms the no reset scheme. We're also looking at different times to perform the reset. So we can see when resets are fast and the physical error probabilities are low, the distance halving effect means that the unconditional reset outperforms the no reset. However, if we go to long reset times or noisy devices, actually, despite the distance halving effect, the no reset scheme outperforms the unconditional reset scheme. Finally, we also looked in our work at if there are ways to improve the performance of the stability experiment if you don't have access to unconditional resets. So we have two different syndrome extraction circuits in the no reset context. One we call error spreading and one we call round squeezing, which achieve improved stability performance relative to the standard no reset scheme, but come with downsides. Error spreading has decreased memory performance, whereas round squeezing requires additional physical qubits. So just to conclude, the answer to the question to reset or not to reset is it depends. In the future, when we have fast, high-fidelity resets, it's clear that the unconditional reset scheme is best, particularly when we're performing logical operations. However, in the shorter term, it may be that not resetting or using one of the alternative circuits is superior. Thank you.
Thank you for the nice talk. Do we have questions? Yes. Okay. Let's see if I'm as good as Christian. Yeah, right. All right.
Hi. Thanks for the great talk. So this is going to be a bit of an experimental question because I'm an experimentalist. So the first thing I think when asked this question, and you've also showed the different construction of the stabilizer circuit, and there was the word leakage in the slide. So the first thing I think is that if my readout happens to have a lot of leakage, that I would like to reset the leakage. But if it doesn't, then I don't have to do that. So, but I saw that in your simulations you only use this like physical error parameter. So I guess what my question is about is the error model that you're using. Are you considering the leakage? Is your unconditional reset getting rid of that? Or like what's the sort of situation there?
Yeah, so in our simulations, we didn't consider leakage, but yeah, you're absolutely right, that will have an impact. I think probably the kind of key messages aren't too influenced by including leakage. So firstly, the fact that the distance halving effect means you will want unconditional resets in the kind of medium to long term. I think that stands regardless. Yeah, if you have the added benefit that your unconditional reset removes your leakage, that's an extra benefit. You're right in the short term that if you don't have unconditional resets, you would perhaps want to be able to remove leakage in other ways. So I know there are schemes, for example, that just return the two states, the computational basis, without necessarily requiring the full reset to zero. So you could view some of the nearer term results as, assuming you have a different leakage reduction mechanism. But yeah, you're absolutely right. Some of those decisions, particularly in the shorter term, will depend on the details of your leakage schemes, the details of your leakage reduction mechanisms, also other different factors of the noise model. We tried to choose something that was broadly representative of some superconducting hardware, but details will obviously vary.
Right, thank you.
Maybe another very quick one. It's right there, yeah.
Thank you for the talk. When you're considering the time or comparing the time between the two methods, does the no reset technique influence the impact on the decoder task, and does it take extra time?
Yeah, good question. So we have, in this case, the timing, we haven't considered the decoding time. It was just done on the length of time to run syndrome extraction. Our circuit times, I think our measurement time was something like, 600 nanoseconds. And so even in the absence of resets, we're heading towards kind of a microsecond per round, which is kind of the thing that's taken for the approximate aim for decoding time. But yes, you're absolutely right. There's no point removing resets, making your syndrome extraction incredibly fast if then your decoder's not able to keep up. Yeah.
All right, let's thank Ophelia again. And this is the present.
Thank you.
Yeah.
Do I take this?
Yeah, I think so. All right, so the next speaker is Stefan Tassler from the University of Erlangen-Nuremberg, and with a title, Parallelized CZ Gates for Parity Check Measurements. Take it away.
So thank you, and also thank you to the organizers for inviting me, and it's a pleasure to give this talk here. So, whoops. So I'm going to talk about parallelized CZ gates, which we use for parity check measurements. And this is a project which is done by the FAU, from which I am, and also from the Forschungszentrum Jülich in the scope of the Munich Quantum Valley. So, so first things first. So actually 2 papers originated out of this project. First, the paper here where we're optimizing superconducting 3 qubits gates for surface code error correction. And the second one is that we were looking also for fault-tolerant stabilizer measurement schedules for exactly these 3 qubit gates. So this is, the collaboration is mainly done with UCS Old, who was supervised by Markus Müller, and also I'm supervised by Michael Hartmann. And yeah, so to get things started, I think you might have seen these in the previous talks, but to just talk about the basics. So what the main goal in designing our 3 qubit gates was to look at stabilizer readouts. So here you can see the Z stabilizer readout and also the X stabilizer readout circuit. And basically these are done as you've already seen. You have data qubits here, the darkish circles, darkish blue circles, and then the ancilla qubit, which you want to measure in the end, and then you encode by applying C0 gates or CZs and single qubit rotations, and then measure the ancilla qubit in order to get like a stabilizer readout and also a syndrome if you do this over the whole surface code error correction code, and then you can determine whether errors happened or not, and therefore you need parity checks, or you do parity checks. So, because you do them quite often, the idea now was that we can try to speed up these kind of like gates by combining these CZ gates, which would look like this here, for example. So first you would apply a Hadamard gate, and then you would use parallel ZZ interactions, which you can engineer between the 2 data qubits and the ancilla qubits in parallel. And then you get an oscillation of your ancilla qubit state, if this is prepared in X basis then. And then you can stop at some point, and at some point then you could like switch off your ZZ interactions, and then you get a perfect parity check, like separation of the parity of the 2 data qubits. And then you could apply these for both, like for both 2 data qubits, and then you could measure your stabilizer. How this would look like is actually, you can see it quite well here with this like toy model like type. Where you have a coupling strength here, and then you have a ZZ interaction, and you prepare your ancilla qubit in X basis, and then you see that you have a state-dependent, like parity-dependent oscillation. For example, even parity oscillates, and odd parity stays just the same. And then you could switch it off at this point, for example, which is like simulated here, and then you can just measure your ancilla qubit, and depending on the measurement result, then you know which parity your state has. In order to verify this, we were looking at our circuit, or we did a circuit simulation of the following superconducting circuit, here where we have 2 data qubits here in blue, 1 ancilla qubit also in red, and these 3 qubits are fixed frequency, and we only apply a flux on these 2 middle tunable couplers in order to drive the ZZ interactions in parallel. We quantize the circuit, we get this circuit Hamiltonian, and then we put this into Qtip and run our simulation and check how this, like how our gate actually works, or how good it performs. And before that, we have to also be careful. We want to implement our gate in a surface code error correction. Therefore, there's a very important thing we have to look out. So we have to look out for fault tolerance breaking errors. These errors, they are existing also for the standard way of reading the stabilizer out. So for example, if you have a Z error happening right in between your C0 gates, then this error will spread due to the C0 gates onto the last 2 qubits. And if you're not careful in choosing your readout schedule, then this could happen that, for example, you have 2 Z errors on these 2 qubits here, and just trigger this stabilizer here, and by this you would correct for the third qubit, and this would create a logical error, which is not very good, because then you did a logical operator, obviously. And by this problem you can circumvent by just choosing a different schedule. For example, this one here. And then you would have triggered these two stabilizer, and by this you would know, okay, so errors happened on these two qubits, and then you could correct for them. However, if we are now looking at these 3-qubit gates, we have to be more careful about these kind of errors, because they are quite more likely to happen, because now we can have also 3-qubit errors, and they can also spread. So one important thing we found out, actually, that we can find a fault-tolerant readout schedule for the unrotated surface code. This is the second paper I was mentioning. This mainly focuses on this. So we can choose our schedule like this here. So these are the CZZ gates we apply. So first we apply these CZ, and then we apply these in parallel. So like these two gates, like these two data qubits. And by this we can find a schedule which is actually fault-tolerant. For the rotated surface code, this isn't that easily possible, because there can't be a schedule found which solves this problem. So we thought that we might differ our gate or optimize our gate in order that it performs still quite well for surface code error correction. It might be not fault tolerant, but it can still improve surface code error correction. So now the question is, which errors are actually harmful? Therefore, we ran 5 rounds of distance 5 rotated surface code using STIM, and then we were randomly placing 2-qubit error, or not 2-qubit errors, but 2-fold processes, so 2 polystrings randomly, and then we were looking whether we get a logical failure or not. And if we get a logical error, then we were just counting these polystrings, and we're also counting the probability, and then summing these up, and by this we could create a weighting of how dangerous such an error is or not. And then in a second step, we created a cost function, which you can see here, so which has 3 parts. So we have a leakage term. This just satisfies that the leakage is still reduced and doesn't get overhead. We have a general term where we apply every poly channel which our gate created. So they would be possible in principle, but for surface code error correction, it's not very suitable.
Makes sense, yeah.
All right, maybe one more. Yes, over there. You can throw it if you want. All right.
Speaking of scheduling,
yes.
Did you experiment with
that we use in this work? We achieved this gate with the double move, so back and forth. We did it with a median fidelity of 99.1%, and the durations. So the duration of the single move, is 80 nanoseconds. The second gate that you need is a CZ gate. So once we moved the state of a qubit to the resonators, we can do a CZ gate between the resonators and the qubits. It works similarly than between 2 qubits. We align we transfer the state from the E1 state to the F0 state, and then back to the E1 state, and the phase makes the CZ gate. We align these 2 energy levels that are here, and this is done as well by sending a pulse to the tunable couplers and the qubit. So on this device, we do it with a median fidelity of 98.6%, and the duration is also 80 nanoseconds. Now the experiment. So we will test the 422 code on our 6-qubit device. So the 422 code is an error detection code that can encode 2 logical qubits using 4 data qubits and 2 Ankila qubits, 1 for X error and 1 for Z error. We wrote here the stabilizers of the code and the logical operators. So I'm going to show you here how we do the circuit for syndrome detection. So first we prepare a state on one of the Ankila qubit. Then we move the state inside the resonators using a move gate. Then we perform the CZ gate between the data qubit and the resonators, and then we move back the state to the Ankila qubit. Then we can measure the qubit, and while we measure the state of the first Ankila qubit, we can repeat the operation for the second Ankila qubit for the X error. So we prepare the state, move the state to the resonators, do all the CZ gate, and move the state back in the qubit. So this is the full circuit where we start by preparing the data qubit into some state, Then we repeat the error detection circuits for multiple time. And at the end, we perform a measurement of the data qubit to check the logical state of the qubits. And this is essentially a memory experiment. So now, here are some experimental results. We characterize first the stabilizers by running once the circuits before for all the cardinal state for the data qubits, X and Z. And we measure stabilizer fidelity around 90% for the X and for the Z stabilizer. The second thing is that we characterize the logical state encoding. So to encode the logical state, we start from a physical state to the data qubit. So for example, 0, 0, 0, 0. Then we run one error detection cycle. And after this, we use the result for the stabilizer to post-select the results. So there will be 50% of the results that are in the wrong basis that are immediately rejected, and about 33% of error that are detected. But so everything is rejected, and then the remaining ones, they are in the logical state, the target logical state, which in this case will be 0, 0 logical. And from this state, we can perform a tomography using the classical shadow framework, where we can see an example here of the 0, 0 logical. And if we do this for all the cardinal logical states, then we have a logical fidelity between 96.6% and 99.9%, and the logical purity from 83.4% to 91.8%. Finally, we do repeated error detection cycles, where we repeat this the circuit for many cycles. So this is an error detection experiment, distance 2, so we cannot correct. So for every error we detect, we have to reject, meaning that as we increase the number of cycles in our experiments, we reject more and more run where we have detected errors. So the average detection rate is 33%. So the fraction of successful run goes down exponentially as the number of cycles of the experiment increase. Now with the runs that make it through, we can measure the logical state. And here we plot the expectation value of the logical state, or the Z expectation value of the logical state of the first qubit and the second qubit. And so depending on the logical state that we started with, we see the correct value with some decay. So this is a decay of the logical state due to logical error or errors that we haven't detected. And we can fit those values and extract the lifetime, coherence time, this lifetime, sorry, and the logical error per cycles for all the states. And all the lifetimes are way above 100 microseconds, and logical error per cycles below 1%. We can do the same for the logical state between the X bases. We obtain this similar rejection rate, and if we fit the expectation values, then we see the similar decay. The lifetimes are a little bit lower, but still above 100 microseconds, and the logical error per cycle are also a little bit worse, but below 1%. So now this is a summary of the results. So we start from physical characteristic of the QPU, which are like the qubit lifetimes and coherence times of the order of 30 to 40 microseconds. CZ gate error and move, so the two qubit gates are around 1%. And then we apply the error detection protocol, and we obtain two logical qubits with the lifetimes well above 100 and coherence time well above 100 microseconds and well above the physical components characteristics. And also the error per cycle is below 1% and better than the two qubit gates. The logical state preparation is between 96 to 99%, and the stabilizer fidelity is 90%. Now, these results, they have been obtained using the scheme, which is kind of a move, CZ, 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 CZ move, where we have to pay this sort of move overhead to bring the qubits into the resonator, the state of the qubit into the resonator. But here you can see that we sort of reduce as much as possible by having a move at the beginning and move at the end and just doing all the CZ in a row. But that's reduce a little bit your flexibility. So maybe what you want is to actually think like the move, CZ move as one gate, and stop thinking of a move, but just call this the CZ. And then you can do all the CZ you want in every order that you like. The problem is that if you use the numbers from this work, your best fidelity will be 98.3%, okay? But the duration is also going to be quite large, 240 nanoseconds. However, we have new devices, a new generation of devices in the lab, and I can show you the best result that we got so far is a fidelity for the move CZ move of 99.3% and a duration of only 80 nanoseconds. So with these numbers here, the graph, the connection graph that I will show you earlier, where you connect all the qubits directly, you will draw all the effective connection between the qubits, this graph becomes much more realistic. And that's great. And I just want to mention that those, so in our lab, we get this result with a qubit as a central element or resonator as a central element. Finally, I want to mention some of communication from our company. There is a workshop on the cloud tomorrow, but there will be also a lot of posters on all the different aspects of the technology on Tuesday and on Wednesday. Related to this talk, there's a poster from Michael and Jakub on the gates from this processor. So I really invite you to have a look. And there is finally a talk on Thursday by Johannes who will tell you a lot of things more in details on the technology and how to scale up. Thank you for your attention.
All right. Thank you, Florian. So we have already one question here.
Thank you. Thank you. Very interesting talk. I don't know if you could go very quickly to the slide number 9. There you describe this energy level. I don't know if you can elaborate a bit more how this, excuse me.
Getting there.
Okay,
right.
Yeah, exactly on the right side. I don't know how you do this control, and these 3 quantum states are representing the quantum bit, the resonator, and would be the ancilla qubit?
Yeah, no, that might be, I went a bit quick. So the ground state here is the coupler. It's the tunable coupler, which stays in the ground state. So most of the time, sometimes it happens that there's a leakage and then the tunable coupler go to the excited state, but that's a bad thing that can happen. But so normally this is kind of transparent, so it stays the ground state at the beginning and at the end.
Right. Okay. And the controlling is like, I don't know how you do it.
The control? Mm-hmm. If you want to measure this, you have to sweep slowly the frequency of the qubits and the frequency of the tunable couplers. So when you do the gate, you apply a flux. So the flux is, so it's a pulse that you send to a line which goes inside the fridge. And then each qubit has some Josephson junctions, which actually there are 2 Josephson junctions, which forms something we call a squid.
Right.
And this is sensible to magnetic field, so it will feel the flux.
Thank you. Thank you.
Yeah, there is one there. Or maybe we can go first there and then there. Yeah.
Hi, thank you for the interesting talk. I have a question. What's stopping you at 6 qubits? Like, can you imagine connecting 100 qubits?
Sure, yeah, I can show you the pictures. It will probably look like that. Oh, you mean maybe all the qubits into one resonator?
Yeah.
Yeah, that's a very good question, actually. We do have one device on the cloud where we have 16 of them. In reality, it has 24, but really 16 that are really good. Above that, it gets a bit complicated because well, you might run out of space, but also adding each of the qubits add a little bit of capacitance to the resonators, so then the characteristics get far away from what you want. Also, all the qubits together add the noise. So this is relatively okay because we have tunable couplers, so we can isolate the qubits well. But there will still might be some noise that will leak inside the resonators and make the characteristic time goes down. So, yeah.
Thank you. It's just a beautiful picture. You can connect like 100 qubits and then do error code, whatever.
Well, but there's another problem, is that you can only do one gate at a time here. So it's great in form of connectivities, but for running the QEC cycles, you need to be able to run a lot of gates at the same time. Otherwise, your QEC cycle, so the times to run one full cycle of error detections, is very long. And then you accumulate all the error. And so it's not really a promising way to do this computation.
Thank you.
Right, first there, and then we have one here in the front.
Hi, thank you for a great talk. I was wondering if you could elaborate on the usage of classical shadow tomography for the logical benchmarking. What kind of benefits do you get in this specific endeavor compared to state tomography?
So I'm not really an expert on that question. So I could point you to one colleague. What I can tell you is that the shadow tomography advantage is that you need less measurements compared to the classical techniques. So it's mostly you gain because you have to do, you have some randomization, and then you have to do less measurements, or less time to compute.
All right, so here in the front. Yeah.
Very nice talk. I was just curious whether you could tell us anything about the Z crosstalk or the microwave crosstalk that you see between the qubits that are connected to the same central element.
Not so much. So we haven't done a very full investigations. There might be my colleagues that are presenting the poster, so they will know a little bit more about that. The feeling that we got so far is that it's kind of okay, because we got sort of between one qubit to another, you get a lot more components. You get one tunable coupler, then resonators, and another tunable coupler, then another finally the qubit. So it's kind of low. For the ZZ interaction. The crosstalk, as far as I know, more depends on the connectivity between all the elements, and your electronics as well can create some crosstalks. So that is, I think, quite close, similar to these architectures. But we can talk more if you like.
Thank you.
All right. Do we have time for one last question, maybe? Or, okay, one.
Cheers. Thanks for a great talk. I was just wondering, could you maybe comment on the relative benefits of using a qubit as a central element or a resonator?
Yeah, that's a very good question. It's still, and we had investigating a lot, one or the others. So the main advantage of the resonators is that it's big, so you can connect a lot of qubits to it. If you want to do the same to put a qubit like this with one qubit at the center with 16 other qubits, it would be very difficult, because first you don't have a lot of space around one qubit, and also every qubit that you add with another couplers, it adds a little bit of capacitance, and then your qubit lose an harmonicity, and then the coherence time and lifetime drop. On the other end, they are also big, as I said. So big means like it's more challenging for the design, in terms of design, to fit a lot of resonators, big resonators into the QPU. But there's also a difference that the resonator is harmonic, and the qubit is non-harmonic. So that might change also your probability of having some leakage, and the physical, what happened physically changed a little bit. So this is still open questions that we are trying to answer. So far it works okay, but when we go deep, the physics is a bit different. You can also use the resonators you can use this multiple state of the resonators as a bosonic elements, and then to use it for your computations. For like some NISQ calculation, you could use it for example, there's a paper about that where you can use it to simulate fermion-boson interactions, using the resonator as a boson and the qubit as a fermion.
All right, so I think there are more questions, but maybe in the interest of time, let's close the session, and let's thank Florian again.
Thanks.
Great. Then thank you to all the speakers and to Alessandro for chairing this nice first session. The next step on our program is we walk outside the door, and there's a small reception, some snacks and some drinks, and then we will be back here at 6 o'clock for a Ask Me Anything session.
No, I think we should all just, we could either walk up, but I think he asked us to just start, even though no one's in there.
Starting means sitting down.
I think we should just all sit down, and then I stand, I give an introduction, and then we go. David, you mind me taking the side chair?
Here we go.
Because then I can moderate everyone easily.
I also did strength training yesterday.
Oh.
Let's see whether I can get up.
You want to sit in the middle?
No. Zoom.
Welcome everyone to this Ask Me Anything session with our lovely panel starring David DiVincenzo, who I believe to this audience does not need an introduction. Then we have Dr. Anne-Marijs Zwerver, the CEO of Groove Quantum, someone from a slightly different field with a focus on spin qubit that hopefully can teach us a lot of new perspectives. We have Alessandro Bruno, the CTO of Quantware, Delft's one and only superconducting quantum chip company, and Professor Frank Wilhelm Mauch, who is also the coordinator of the Open SuperQ Plus project, which is uniting most of the European side of this field. So with that, I'd like to kick it off. And this is an interactive session. That means that I will be throwing around this microphone to people that have questions. But I can imagine that we need some icebreakers. So I will start with some questions to our expert panel. So I will start with David, since you are the title of the session. And we had a very nice conversation in the hallway before the session. And one of the questions that you triggered was, what ideas are out there currently in the space of superconducting qubits and algorithms that are currently really underexplored, underrepresented?
Okay. Well, I can throw out a few ideas, but I don't think I have all the answers. We can try it with everybody, but so what is underrepresented? I guess what's very sufficiently represented is error correction at the moment. I think there are enough of you who are on top of that case. I guess one is the whole problem of systems engineering and, for example, cold electronics. And can we eventually put the whole control system into the fridges? I think that remains an interesting and important subject. And we discussed RSFQ. How many people here, this is always good to get people woken up. How many people feel they have a pretty good working understanding of RSFQ? Okay, that's not a huge number. Okay, so I recommend some training on that point, because that has had promise for many, many decades as being the way to make cold electronics, using entirely superconducting phenomena for the switching devices. Let me stop there. I hear some. Oh no, that's a side conversation. Okay. Okay, Adrian, I'll kick it back to you then.
Good, thank you. So, are we woken up enough yet to have an audience question? Yes, I see one here.
So,
for who's the question?
Oh, do I have to specify? Okay.
I can also direct the question.
Yeah,
Maybe
thank you. So my question is mainly like, I'm thinking maybe the qubit is a bit flawed in the way that it's not adhering to the natural phenomena of like an atom. So if we want to do true quantum mechanics, in what way is a qubit limiting us by perspective of only looking at two-level systems?
So let me feed that back to you. So you're saying what is limiting, given the kind of quantum systems we use, in what ways are they imposing limits on us that wouldn't be present if we had really ideal two-level systems?
Yeah, and what are we, like, it's a bit more specific at the question from Adrian. What are we missing out on if we would look at the true atomic nature of our qubits?
Okay. I'll again try a little bit of that. Part of what that connects with is the fact that our real quantum devices drift. Of course, the atomic physicists are always proud of saying, oh, we have rubidium atoms, and rubidium atoms are rubidium atoms. And you guys have got these dirty, junky devices that are different every time you sneeze at them. I've never thought that's such a sharp critique in the sense that they have to make their rubidium atoms different on purpose because you have to actually address each one, so that it has to be somehow different in some aspect, the fact that it's here in space and not there, and you have your control beam, pointed at that and not at something else. And that always brings in, these aspects of the real world, like, jitter of the laser device and things like that. But I guess that tomorrow, I believe there's, tomorrow there are whole sessions about materials and, getting that right. And I guess that's one of the many things that we, this community has to get right, is keeping the qubits sufficiently under control. They're never completely well behaved, but they have to be, good enough. And there are plenty of quantum devices out there that are not good enough and have never been good enough, and they, has taken decades for them to be good enough to qualify as qubits. I don't know, does that get you somewhere on your question? You don't have the cube anymore, though.
I think this is a very nice bridge that we're talking about different qubit modalities for Annemarijen. And what I'm curious, since you're here sort of in the den of the wolf,
yeah.
What lessons can we as a superconducting community learn from the spin qubit community?
Wow. So I have to be arrogant right away. Okay. Let me think about that. So way back, in the way past when I started at QTech, I remember there were 4 modalities. There were superconducting qubits, there were Majoranas, there were spin qubits, and there was diamond. And I remember we had a meeting every week where 1 or 2 people would present their work from the different modalities, and then afterwards we had a lunch and we would all discuss with each other. And most of the time when someone presented something, they also presented a problem. And then at the end, during the lunch, someone from the other modalities would come to them and told them, hey, actually we had the same problem a year ago and we solved it so-and-so. And that was so helpful. And somehow over the years we grew, right? And we grew apart as well. And I think that's actually a shame, because I think there's a lot to learn on very small things like error mitigation. You have completely different errors than we have. We have a lot of electrical noise coupling into our devices right now, for example, but we're looking at that. And at some point, I can imagine that you want to have just that extra 9 of fidelity, and you have to look at electrical noise as well. And then probably we can, learn a lot from each other.
That was not an arrogant answer.
I'm trying to be modest. And then secondly, I think that might be more arrogant, but what we're looking at a lot right now is more than next neighbor, beyond next neighbor connectivity. With spin qubits, we can do that relatively easy by shuttling a charge carrier, so an electron or a hole across a device. In theory, all-to-all connectivity, but let's just say more-to-more connectivity, which obviously, brings a need for the redundancy and error correction down, and this is maybe something that we can all look at together to have more efficient error correction protocols in the future.
So the first part of your answer triggered something with me, is we're seeing this trend now with SQA, which I'm a big fan of. I see Frank raising hand, so maybe you want to go first?
I don't know whether I should go first, but I have also on all those questions, I would like to put out a provocative statement that holds for many qubit modalities, which is surfaces are evil. And what is nice about superconducting qubits is that in a very simple description, they're very independent of microscopic details. Anderson's theorem. Who of you knows Anderson's theorem of the theory of superconductivity? Very good, a few people. I won't quiz you on what it is. So it says that the thermodynamics of a superconductor are in lowest order independent of elastic disorder. So the diffusion constant does not appear, of your material does not appear in your qubit properties.
But magnetic materials are evil.
Yeah, yes, they are very evil, but we see a lot of noise sources come in the surfaces. Heterostructures of semiconductors have surfaces internally, and I recently had a nice conversation with Jean-Michel Gérard on how these things that look nice all fluctuate. And the ion trappers, when they make 2D traps, they are now discovering all of the lovely problems of surface physics. So it seems to be a little bit to me that when we start with a natural qubit like an ion, I cannot make the same statement for neutral atoms right now, but if we start with a natural qubit like an ion, when we build a system, when we want to large-scale integrate, we are getting nasty surface physics and human-made components anyway. Between the different modalities, they appear at different times, and spin qubits had to deal with them from the ground up, so maybe they are so experienced with dealing with this that they solve these problems before us and overtake it. Who knows? Who knows? Sorry for interrupting you.
You're always welcome to come and talk.
Well, I think the nice thing is that what you're just raising as a point connects very much to the question I had for Anne-Marie, following up on the first part, which is sort of what we're seeing now also with this conference, and I like this conference a lot, is we're now going more and more into our modality-based silos, and we're always sort of having this our modality is better discussion. Is there not some kind of way that we can bridge this gap, and is there anything very practical we could do to make sure these lessons learned in, let's say, in the 80s in some old modality or in a different human modality that you've solved all the surface problems, how we make sure that this shared and those lessons land?
Is it working?
I think so.
Yeah, so I think this multimodality, it's a bit of a jargon, but it's also ultimately a necessity. I mean, there are so many variants of approach and materials and platforms that with all the pros and cons, in the end, the solution may very well be a mix of everything, where there are memories made of, I don't know, floating ions on some trap that indeed they also suffer their surface magnetism maybe, and then some charge carrier that are there to shuffle information around. The nice convergence is that more or less we are all in the quantum. Cryogenic is actually an asset. It's not anymore this daunting extra piece of hardware that you have, but I mean a dilution refrigerator is somehow not even the biggest part of a bill of material, and within a cryogenic environment there is plenty of space to mix the technology also with the classical ones. So I think the future is definitely multi-modality.
I'd like to address one thing, Adrian, that you asked about, which is how do we, avoid staying in our silos. And for me, a partial answer for that is for us to remain interested in the basic physics of what we do. Because when we work at that level, then we're working at a higher level and we have ways of communicating with other people. Of course, we have to be deep in the details also, but if we come up and say, what principles is this based on, then we have a way to connect with others. The trouble is that only works with the physics part of our field, and our field is not only physics, and you should be a computer scientist to think about the algorithms, and or you should be a mathematician to think about the error correction codes.
Engineers.
And I don't know if we can span that far.
I think the engineers have a big piece of the cake as well.
Yes. Yeah, I think that raises the same question. I mean, we're now talking about the silos of modalities, but even, for instance, within our company, I can sometimes notice the siloing of the microwave engineers and the cryogenic engineers and mechanical engineers and the quantum engineers, right? And we all speak different languages. So is there maybe someone here who has some tricks how we can, well, if the common language between modalities is physics, what's the common language between disciplines that makes us quantum? I see you're compelled to answer that, Annemarij.
Well, it's something I'm trying to think about on a daily basis as well, and I don't have the answer. That's maybe my answer. A couple of things I'm always thinking is I'm trying to see it not as a competition, not between different qubit modalities. We all want to get there in the end, and I think together we can make each other way stronger. If one of the qubit modalities demonstrates amazing new milestone, that's actually good for all types of qubits to get more attention, to get ahead. On the other hand, maybe also within a company, it's not a competition. It's not who makes the best waveguide or who makes the best, I don't know, cryo CMOS. It's how it all works together. And yeah, I'm not sure if that's the answer, but at least it's not a competition. We should have an enthusiasm to get there together and just talk a lot. I always believe, and that's very cliche, that the hallway conversations are the most important ones.
I'd like to give the audience a question. Philip, you had a question for a while.
Hi, yes, thanks. I had a question which is kind of maybe taking us 3 minutes back in conversation. So we were talking, there was a discussion about problems with spin qubits, and this reminded me of something that David was talking quite a lot a couple of years ago, and I wanted essentially to ask a question about updates. What are your views right now, and maybe what are other people's views right now? So you were giving a couple of years ago talks essentially about weak arcanomicity of transmon qubits, and how because of that there is essentially, you're talking about the spaghetti of large number of higher excited state interacting with each other, and how at the time you know, you were discussing how IBM without at the time couplers were balancing very close to the onset of like quantum chaos regime, and how other devices with couplers were further away from that kind of quantum chaos regime. And you were pointing out that this is, that was kind of still very much an open problem. And now we have, since then, we have seen results from Google where they are doing error correction, and they have some special modules to eliminate leakage errors. And you know, and they could do unconditional reset, reduce some leakage errors. And I was wondering, like, with these new results, or you know, essentially, how is this perspective of onset of quantum chaos on quantum processing evolving right now? Is this still a threat? Are we still like balancing at the edge, or are we? Is that threat kind of with technical developments going away?
So yes, I think I can answer that in the sense that I had indeed just one paper, no, 2 papers, I guess, on this exact point, and basically in attempting in a friendly way to knock IBM, that they were choosing parameters that looked kind of dangerous. But I think, well, of course, they, in the meantime, have evolved away from that, you know, that dangerous boundary. But I don't think there's any general prescription in the sense that we have to use quantum systems that are a bit on the edge, right? That you probe them, you do something to them, and they change, and they get entangled and things like that. It's no use using, as well, I guess John Martinez will always say, we can't use neutrinos for qubits. We can't use you know, otherwise perfect quantum systems that you can't manipulate, and the fact that they're manipulable means they have to be a bit sensitive. And so you have to find this balance, and I don't think there's any abstract way of doing that. I think, you know, you who go in the lab, you have to go in and you do it, and you just see if your control schemes work, and you try to use them as best they can be used, and you find out, oh yes, we really do need to use tunable couplers. And now we hope we don't have to use anything more than that. It seems like it's evolving in a good way, but I know that the question that I continue to look at, you know, every time I see one of these amazing new advances is, are we actually making progress on error rates? because that is sort of a bottom line, that everything will be driven by that. So I'm very pleased with papers where I see painstaking studies of error budgets. This much of it is due to the guys sneezing in the lab, and this much is due to the 2-qubit thing, and this much is due to leakage and so forth. I think that there's no shortcutting that. I think that has to be done very painstakingly, and you keep squeezing on it. And maybe we're close to the end of the squeezing. I keep looking at Nathan and whether Google feels it's finished with the squeezing or not. I believe no, and I also suspect that if you commission a new system or something like that, then you have to do this all over again, right? That you've suddenly stepped back by 2 years, and everything has to be re-squeezed again, retuned. And you just hope and pray that you will indeed get back to where you could potentially get to, that you had in the old system. So I don't know. Does that's my own take, of course, as a theorist of where we are with these kind of issues.
I'd like to give one more question to the audience over there.
So I had a general question. I was wondering, how do the panelists like to define quantum advantage? And do you think that quantum advantage will be shown before full fault tolerance?
Ale?
You might want to specify.
I think the new buzzword is quantum utility.
Yeah,
That's where we are more aiming
But I call
at.
it quantum practicality.
I guess in the end of the day is the moment when a quantum computer will make some money for someone or save some money for some big endeavor. I guess it will always take a lot of qubits, a lot of good qubits, a lot of smart people putting together a very big system. That's kind of inevitably.
There's probably an answer from governments that is a little bit different, that wouldn't measure it purely by money. I'm gesturing to Frank because he knows what governments think. Maybe.
You're completely overestimating me. I mean, we can ask how would we know that we are there, and I don't think it will be a sharp transition. Because, we see those cross-entropy benchmarking results. They are like the drag race of quantum computing. You pose a completely artificial problem in which quantum computers happen to be good. Or it's the Formula One race of quantum computers. It's very self-referential. Then, on the other hand, you could say, when will they outperform classic computers on something useful? What is useful? That's almost a philosophical question. So let's go in between. Let them answer a question that we would have even if we didn't have quantum computers. So then we are maybe coming to an area where people start using quantum computers in theoretical chemistry and materials science and think they are useful even though retroactively they could have done everything classically. But for me, it's maybe when we use quantum computers to do something, to do a modeling task that we wouldn't have done in a classical computer, even though retroactively we could have done it. That would probably be a definition. It should be a question that we don't have just for the sake of using quantum computers, and let's please avoid the word usefulness, right? If we do it in financial market modeling and making some people who have a lot of money even more money, I don't want to enter a usefulness discussion, at least not on this stage.
I think it's interesting, those who are students of digital computer technologies and their advancement, you can ask the same question. When was their digital computer advantage? And I think depending on how you set up that question, it can be anywhere within a period of about 25 years.
I've just published a piece in a magazine for German, I think, IT managers. For those of you who are German, it's T3N. And I claimed that was in 1943.
40. Okay.
When Alan Turing broke the Enigma and probably shortened World War II.
Right, and then but you could also answer that it was in 1966 when IBM started to turn a profit on their 360 series.
Yes.
And anything in between. There are many milestones in between. Yep. And many people lost lots of money in those times also.
I see a question all the way in the back. All the way over there.
Just throw it somewhere.
Let's throw it into the audience, and then we'll see if it gets all the way back.
Big throw. Whoa. Halfway.
Okay.
This is part of the experience.
Okay, thank you.
Swap network first.
As we've seen in the talks today already, a lot of companies are investing heavily into quantum computers, such as Google, IBM, you name it. But in recent years, some of the promises that quantum computers were supposed to provide us, such as protein folding, some advances in chemistry, as you alluded to already, were solved by machine learning models. And I am wondering whether if you see any, I'm not supposed to say useful, but
you can.
Okay, I can. If you see any reasonably reachable applications which will not be which we won't be able to solve by other means. I mean, we can probably at some point break RSA encryption with quantum computers, but at that point, those algorithms will be obsolete anyways. So what promises do we still have which will keep companies interested?
Theoretical chemistry. No, seriously, because I think the competition with... So first of all, the competition, the different modalities make progress, and we don't know who is how far is completely healthy and normal. But I think if I speak very broadly, simulating other quantum systems digitally has the most acceptable compilation overhead on quantum computers and a very bad one on classical computers. But I think when we talk about advantage and roadmaps, we need to make sure that we're not completely taken away by what our sponsors want, but that we are rather, doing also a bit of expectation management.
Yeah, I can admit I've always found this quite an obscure question. I mean, it's terrible to admit. And in this small group, I'll admit that I don't really know what a quantum computer will be useful for. But I worked for IBM and remember this famous thing that the IBM chairman said, this computer will be useful for 6 things or something like that, or 6 customers will need it. And one hopes that other people, and maybe not indeed the people in this room, not mainly the quote hardware people, but I gather there are really some software and algorithm people in here that they'll save the day for us.
Maybe we could also pass the same question to one of the middle chairs.
Yeah, no, I actually agree with what has been said, and I sometimes say to people, 50 years, 60 or 70 years ago, we didn't know that we were going to take photos of our food and post that on Instagram and use a computer for that, right? We mainly, I think, firstly invented it to calculate ballistic trajectories, and yeah, there's so many things in the future. Maybe even a quantum computer can do things that a classical computer can do as well, but just way more efficiently. I hope we're going to use it to mainly do good things and regulate that. And I'm actually quite excited about what we can do. Just as with the normal computer or classical computer, we didn't know what we could do today, basically. I'm pretty sure. I believe in quantum computing. Let's say it like that.
My vision, maybe it's a bit more, I think quantum computer may be co-designed or designed by some, well, AI is now an inflated word, it's not just LLMs, but maybe philosophical, but we also need to be humble. I think we don't really understand how to use quantum mechanics to find all the shortcuts, because we are still exploring the world as scientists and researchers. And maybe a mix of computer-aided design and The point is that also not only the design, but also the users, I mean, the interpretation of all the readout, error correction, and results is also in the hands of some algorithm. Then what really matters is the question that we asked to the quantum computer, right? And
are we at 42 yet?
Yeah.
I want to give sort of a science fiction answer to the question of, what will this be useful for and so forth, but which I don't mean completely as a joke. So, of course, we see the rise of large language models and AI, and these will be placed in supercomputing centers, and supercomputing centers currently are planning to have hybrid structures where you plug in alternative machines, including quantum processors, into the supercomputer, and then we'll start interacting with this chat QGPT or something, or it won't be labeled as quantum necessarily. You just said this model is given access to the entire supercomputer to solve problems. And we'll start asking questions, and it'll start solving problems we didn't think, gee, how did you solve this problem? And it will turn out that the AI will figure out for itself how to use the quantum computer, and then we'll never know how the quantum computer is giving advantage. But it'll just somehow become so because of the freedom we give to our AI devices.
I see a question all the way in the back. I think we could throw the box again.
I will try.
Relay.
Okay.
Yeah, perfect. Wow. Oh, no.
Amazing. Thank you very much for the answers to the previous question. In that regards, instead of looking at the future, I would like to ask a question about the past. I always hear that one of the strongest arguments for building a quantum computer isn't about what we can do, but what we have done in the past, in the sense that it has done tremendously in the level of quantum control at the level of classical hardware, but also at the level of classical algorithms, how much we've pushed ourselves in order to compete with the quantum computer, with the classical computer, just because somebody wanted to do a classical algorithm as good as a quantum algorithm. And you guys are really clever people, so I think I'd like to ask you, what has been the biggest breakthrough that trying to build a quantum computer has already made in the past maybe 30 years?
So I'm looking for a volunteer here.
That's an easy one, but
You mean the biggest breakthrough in unintended applications?
Yes, I think it has to be unintended. Otherwise, everybody's thinking about Shor's algorithm or trying to earn money.
So let me just start with the disclaimer. One of my postdocs is currently starting a company that commercializes a quantum-inspired classical algorithm, and that will be great. But on the hardware side, you should really check him out. His name is Tim Bode. But on the hardware side, let's look at what measurement capabilities are doing to other points where we would really like to precisely measure microwaves from our field, like all these detections, for example, in astrophysics, because it's bringing together techniques from atomic physics, but now for artificial atoms. That is certainly moving science, and that's always great. Maybe not the greatest application, but I thought I'd start.
Yeah, I think from the perspective of quantum devices, I was doing theoretical work on quantum devices before there were qubits. And, they involve things that superficially are things that the two of you who work in the lab know very well. You grow films of things and you put wires onto them. And the stuff that was were being done in the 80s from today's perspective were junk. Were just total crap. It was amazing that you could see anything. And the improvement of those as a result of pursuing it using the qubit paradigm has been just unbelievable. Just the precision that now exists in the study of quantum phenomena in solid state devices is incredibly enhanced. I don't think we've yet really come back to the fundamentals again and seen what new things it does for us, because we've been so busy pursuing this qubit paradigm.
Maybe we could also point to tensor network-based algorithms, which have certainly been enormously pushed by the quantum community, and you can now, in classical computer science, you use tensor networks for many things, and oftentimes by It's done by PhD students who wanted to solve the classical counterpart of their quantum PhD problem first, and then did a whole PhD on them. Let's, for example, I have the honor of co-supervising an industrial PhD student who does fluid dynamics with tensor networks and does amazing things with it.
And it might be a moving target, as you said. Every time things are getting better and better. I actually thought about maybe the first time someone had Shor's algorithm, but now when I think about it better a little bit, what I think was a very, well, to me personally, a very interesting milestone was the violation of Bell's inequalities using the quantum internet. Yeah, basically demonstrating physics with quantum technology, to summarize. Yeah.
I think we're also getting to the point that, I mean, many of you are, of course, familiar with Richard Feynman, and back in the day when we talked about thought experiments, and everyone thought, well, these are crazy ideas because you cannot manipulate individual particles, entities, anything, to actually do these thought experiments. And as you mentioned, now we're actually doing that in the lab on a daily basis because we're trying to build a computer. Which is kind of crazy, especially, and I don't know about you, but for me personally, there's an aspect that really drew me to the field back in the day. I am once again looking at the audience for more inspiration. I see many questions now in the front 2 rows. Let's take them back to back.
Third row.
Third row, and then first row. So the lady in the third or fourth row.
Yes, I'd like to bring it back to the materials really quickly because I work on the materials. There was a statement that surfaces are evil, which I think is a good statement. I hear it a lot. I wanted to ask a more general question first about what you think are main bottlenecks that I should focus on, but I guess the answer will be surfaces. So then my question would be to anyone who would be interested to answer, if you could order any surface for me, what would you like to order?
Maybe as I've so first of all, I should say I'm a theorist. I do the most advanced fab work of my life I do on Saturdays in our home kitchen. But I mean, first of all, in surfaces, we have, for example, seen work on encapsulating surfaces to get to control surface spins. That is, I think, that's, I think, wonderful. But coming back to the materials question, that's also because of the genius loci, because here the first flux qubits were made. Again, we should always keep in mind that we are in the beautiful situation that in superconducting qubits we're using collective electromagnetic degrees of freedom. Even if we say here is a change of a Cooper pair, it's a collective electrical charge that happens to be 2e. And I mean, for improving surfaces, we just need to, you know, I think it's arduous engineering. So I don't have any genius insights, but I think in terms of encapsulation, there were these experiments. I don't know how much people have followed up on this, but there were these beautiful experiments by Robert McDermott about 10 years ago, where he first found out that there are spin glasses on the surface by unsaturated oxygen bonds, and that he could get rid of them by encapsulating this. But this process didn't scale, and certainly not in Robert's lab. But maybe, you know, it shows that things can be done about surfaces, I think. I don't know, maybe for all experimentalists, they said, oh, he is now telling us the news of 10 years ago. We are already doing it, or he doesn't know how stupid it is. But Alessandro can criticize me now.
Well, I guess it's, what you said is true, but also the advancement, the encapsulation doesn't really remove the problem, I guess. When there are electromagnetic fields, there are always currents on the walls of the conductors that support these fields. And so if you are a Cooper pair, maybe you're doing fine, but there are many two-level systems of many different origin. Some are even due to Anderson localization, some are just atoms missing, strains, substitutions, and quantum knows what. I guess there are advancements on many aspects. Encapsulating is one of them, but there is still no secret sauce, because even just a few defects per square micron can make the device be, well, the particular qubit be not available for computing. And then there are, as soon as we keep digging into the materials, you see that there are many other effects at play. When I think of superconducting or a cold piece of silicon in the cryostat, I actually see not a Cooper pair superfluid free of flying. Many times I think about nuclear explosions with these high energy cosmic rays that are putting a huge amount of phonons, and there are recombinations. There are many other things that actually I wonder if it's only prone to this community of superconductivity, or at some point it will manifest itself in crazy errors on spin qubits, or why not even ions feeling what's happening in the substrates, because we need substrates for everything we are doing. And we are literally under the sky.
I think on the long run, there's a question of resolution, right? We need to eliminate the leading sources of noise to discover the subleading ones. And I'm torturing colloquium audiences with my favorite Sherlock Holmes quote. You know, how often do I have to tell you, when you ruled out the impossible, then whatever remains, however improbable, must be the solution, which brought us the cosmic rays. We should keep in mind, you know, I am very old. And when I started my postdoc in Delft in 1999, and across from here there was a supermarket that was open until 10 p.m., the question was, A, if we put a squid next to a flux qubit, does this kill quantum coherence completely? And B, will we ever get T2 beyond a nanosecond? And that shows you that nothing of what we're discussing right now was even anticipated, even by wise men like my boss, then Hans Moy. So
the supermarket is still here.
Yeah. Is it still a C1000?
No, now it's different. Maybe.
Okay, very good.
So I was interested to ask Anna Maria, is germanium on your mind in the sense of, do you desperately need isotope purified germanium to do something better?
That's actually a good question. So we're using a semiconductor germanium instead of silicon. What we've seen in the silicon community for the silicon qubits, when we isotopically purified it, the fidelities went up with an order of magnitude and even more. For germanium today, we already have an order of magnitude higher fidelities than we have in silicon. So to that aspect, you could say not necessarily. Then again, ideally we have, it's never good enough, right? It should always be better. And if you anticipate what we've seen in silicon and basically copy that to germanium, germanium actually has a little bit higher abundancy of non-zero spin isotopes. So then if we purify it, we might even get an order of magnitude or more up in fidelity as well.
And it's probably a little worse just in irregular impurities also, I suspect, because I recall learning that germanium comes from, it's often mined together with lead.
Yeah,
so
lead
you have a bit of lead in your germanium, which doesn't sound so friendly.
Yeah, that doesn't sound friendly. That is something we actually don't encounter. What we do encounter, interestingly, is that if we purify it today, we try to purify it, we actually purify it chemically, because indeed it's a byproduct in zinc and lead, etc. Then suddenly it's a very pure germanium, so isotopically purified, but we have a lot of chemical isotopes now, so hydrogen and oxygen. So then we have a problem with that. So purifying is actually a bit hard.
Yeah. I'm not sure if that was the question, but...
I think we have another question here on the first row.
I think you kicked it off quite nicely, Adrian, when you were discussing about the idea that there's something missing, maybe, and like what's interesting that might be missing. I kind of want to maybe look at the opposite of that question, and I think it's something that David was hinting at as well, about do you think there are certain architectures that have, excuse the pun, reached their lifetime in terms of scalability, and we kind of see the arc of its trajectory, and how far it will be able to push us. And maybe there are more interesting potentials to look at in superconducting qubits that might offer some more surprises for us. Or do you think we've kind of understood the theory enough that we can kind of think about where things are going, even if we change our architectures that we work with?
I don't know. I think there's still many potential pathways. I don't know, architecture means different things to different people, so I'm not quite sure.
Let's say transmons. Do you think the transmon has kind of reached its lifetime in terms of understanding how well it can scale and what the limits are be? And it's a system engineering challenge at this point? Or are other architectures maybe more compelling to scale?
Not necessarily, in the sense that, you know, transmons still have the potential of hosting very exotic objects like, you know, cat qubits, GKP, you know, you name it. So there's still, it still has a state space that, I mean, maybe we won't do that. Maybe FOC encoding is the way that we will go. I mean, that's what 95% of the effort is pointed towards. But I don't think it's a done deal that that it couldn't be some other alternative way of using transmons. Okay, now architectures, I don't know. I mean, I could just be now repeating things that you could all read about, you know, because I follow what IBM is doing. Only, you know, I used to work for IBM, but today I have no special connection with IBM. I just, you know, listen to them and hear what they're doing. And they, of course, have quite ambitious hardware plans for making their architecture more efficient. You know, but at the cost of having couplers to you know, ninth neighbor qubits. Somebody had a slide on that today. I mean, just it's easy to draw a picture of it, but I don't really know how hard it is. I mean, they show a little bit of the multi-layer stack and the adding to the multi-layer stack that they have to do to have such couplers. I think it's incredibly daring that they say that in 4 years, or 3 or 4 years, they will have a whole product based on this basically unproven, you know, concept, which will, you know, in theory, fantastic. You know, it'll make the architecture much more efficient. So I think that the subject is still pretty wide open. You know, one possible history is that we'll go 3 more years and there will be Starling, and you know, we'll all be amazed and we'll say yes, and okay, yes, we all knew that we could make a large-scale quantum computer, right? Well, I don't know. Maybe we do, maybe we don't at the moment. IBM's been very good at putting green check marks on their roadmap for the last 10 years or so, although I think it's a bit of a forced fit sometimes. They give themselves a green mark when in fact it's green by some interpretation, but not by, well, not by all possible interpretations. But I don't want to also beat on IBM. I think they've been good about leading and actually saying things that they will do compared with other organizations which aren't so specific and, well, leave themselves a little more freedom. But, well, give themselves an easy ride in the sense that, well, they haven't really promised anything. And we just continue watching them year by year, seeing what they're doing. I'm looking at somebody over here, in fact.
Could I ask one quick follow-up? Since you've now written the book on circuit theory, is there anything that you still get surprised by when you look at new things?
Is there anything that what?
Now that you've written the book on circuit theory, literally, with your notes that you've put out, is there anything that you get surprised by in circuit theory when you start looking at Hamiltonians and looking at new circuits?
Well, I've written lecture notes on circuit theory, yeah. I continue to feel that's a method that's still under development, in fact, of the, you know, that the full application of it is still still to be accomplished. But I think it's proven itself to be very valuable. I always, you know, what comes to my mind is always the warning that, please, you know, when you do circuit theory and you go through the steps of it, all rigorous, very rigorous, very rigorous, well, but they're never, all steps have some, you know, degree of non-rigor, and you always have to be a little careful. And of course, the step where you say, oh, now I make a rotating wave approximation, watch out, stop, think very carefully. I think it's a beautiful tool, and I've enjoyed it just as a piece of pure theory, actually. And but I think it has very good application, and can help us sort out the way forward. But it won't always. It won't answer the really big questions.
Let's look at the audience for some more questions.
Oh, way over.
All the way on the right.
On the steps.
Yeah, I see.
Oh, we got there.
Thank you very much. Very valuable insights. My question goes on, I don't know, 3, 5, maybe 10 years from now. Imagine we are having hybrid environments with various platforms, superconducting qubits and ion traps and so on. I don't know, I would like to have your thoughts how you visualize this interfacing. Do you see some quantum communication across these platforms? Or do you think these platforms are going to be dedicated to certain workloads and working independently?
Well, I
so, for example, if you have some quantum processor based on superconducting qubits and another quantum processor based on ion traps, for example, and I don't know if you visualize the quantum state transfer between these two elements or quantum systems, let's say.
I think the building blocks are all kind of proven. I think you can go from microwave to optics domain. There are also commercial companies working on it. You can go from microwave to spin. I think microwave resonator are a part of a spin quantum processor. I think, I don't know why I look at you for ions, but
very immature compared with what goes on in one processor, I would say.
Yeah, but still I would say it's it would be easily used in conjunction with other technologies. So I think it's inevitable that that the transduction will be introduced and be part of even a design of an architecture, which is not just siloed in, okay, we have the transmon and we want to brute force because we need utility. I think that's us trying to directly get the big picture, which seems to be within human technologies, let's say. Probably if you ask now to make a 1 million qubit machine with error correction, maybe we can do it, but with infinite money, we'll still require this 5-10 years. If we just relaxed and realized that we are students and or professors, and we don't, well, okay, the big price is important, but actually there will be many other steps, maybe many other interactions, discoveries, new architectures, new modules, new connections, better coherence, better codes. I think the fact is that there are so many avenues for discovery and development that that's why we're here as a community. There will be breakthrough, hopefully, helping to go toward something that will be defined as we go. Now we can pencil out how many kilowatt and how big is the building for a utility scale quantum computer, but the details, I think, will still require doing the right steps in the direction. And well, as an entrepreneur and with how company goes, obviously maybe not all the company will reach the end line. Maybe will be a big corporate, maybe will be an ecosystem. But I think it's inevitable that there will be a lot of brain involved. Because
so a question here.
Maybe I can quickly say something to this question. I mean, the one thing is entangling different objects, physically different objects, like an ion with a transport, is utterly fascinating. And we should absolutely do it as much as we can, just for this reason. The rest, we could actually drive by necessity. At which point does it make sense to do that? For example, if I'm building a big superconducting quantum computer, I want to avoid optical links as much as I can, and when I really need them, I want them please to be ready. And think about PCs. 15 years ago, those were hybrids. They had a magnetic, an optical, and an integrated circuit component. Now it turns out that the necessity doesn't exist anymore. I don't have a CD drive or a hard drive anymore. So maybe for the rest, we can just be pragmatic and see where is it most useful. And maybe it's a good role for theory to find out at which point is a heterogeneous architecture so powerful that it's worth to go through the pain of the interface. And then there's quantum repeaters. And now the next person should ask that question.
Thank you. Yeah, maybe following up on what Alice said, and also like some thoughts about or views on IBM, and also the discussion about the silos in the beginning of the session. I was wondering, like, with the coming of these large industrial players who sort of have the same goal, like building a quantum computer, but also maybe bring a bit of secrecy. And of course, it's great to see all these companies also giving talks in this conference, but how should the academic community deal with that? Like, should they still also really have to focus on building a large-scale quantum computer, or should they be more like explorative, or maybe a very open question?
This one feels a bit for you, Frank.
Okay, so I have a very clear opinion, which is academics should build quantum computers as large research instruments, which have a slightly different set of goals as a large commercial quantum computer. We want to have more transparency, we want to have fewer secrets, and maybe we want to have a slightly different balance of tools. We probably want to have them high fidelity as possible as a non-trivial size and not quite play the size game. In terms of secrecy, so academics can be secretive, right? We all know that. But I feel that currently there are a little bit too many things that need to be reinvented and redeveloped in many labs that would benefit what it's ultimately up to do, which is the struggle and the fight of humanity against T2.
So we're almost at the end of the session. So I'd like to go over all of you and ask for some nice closing remarks. We could do this at random, clockwise, counterclockwise.
Okay, have a nice dinner and talk deep thoughts about quantum mechanics.
I just think it's amazing to open up a little bit between communities again, just like it was. And I also just realized that I wish I was there from the beginning, basically, until now. It must have been, and I just thought about that a little bit, amazing to just basically lay down the groundworks of what a quantum computer should actually adhere to, and then many years later, someone does that in a day to tune up their qubit and basically checks all these boxes.
Yeah, but then you have to be really old. I'd rather be your age, Anna Maria.
I'm sure that we will do a nice exchange of information, and we will learn a lot in these days. Looking forward for discussing technical or visionary things. I think SQA is a great opportunity for all of us.
When we look at the future of quantum computing, we clearly don't have all the answers, and I'm pretty sure we don't even have all the questions. I mean, think about how amazing an iPhone would look like even to a person from the year 2000, we wouldn't have even thought about questions we have about this technology. And when I retire, we will look at this period with a similar thing, you know. Oh, there were all these topics, but those weren't the real topics.
So, with those closing remarks, I'd like to thank all of you for this amazing session. I think also thank the audience for their participation. There's a few logistical remarks. This venue will be closing after this talk, so I would like to ask everyone to pick up their coats and gently go outside and find a beautiful place, go for dinner. There's some very nice restaurants around here, so I'm sure you'll have a great time. And I also have just been handed over some thank you gifts for all the panelists. So if I can give a warm round of applause, then this is it for today. Yay. I have one box. Yes.
That one's easier.
One box of chocolate.
Okay, yeah.
Oh, I know this chocolate.
Oh, yeah, that's good.
Tegeltjesspruiken.